while the other videos emphasized square roots a little bit more heavily, we do at this stage want to incorporate other kinds of roots. And we can extend the comments that we've made, such as the unlocking business, that power on the outside or underneath has to match up with the root, and then we can unlock things. And we have the shortcut way of trying to address dealing with roots, and when we have variables and other numbers showing up that might not simplify quite as nicely right off the bat, as well as some of the other arithmetic that goes on. For instance, we'll come back in a little bit to the rationalizing the denominator sort of situations and say, what else can we do with those that we haven't quite yet discussed? So we're kind of adding a level of complexity here that our earlier class didn't necessarily incorporate. So these other kinds of roots, like the first one here, yes, again, we had discussed how we can use those fraction powers to more directly calculate our answer with the help of a calculator. But again, since there's that connection there and we can use our other rules for exponents, sometimes we can get a more direct answer without actually resorting to the calculator. For instance, this example here, the fifth root of 7 to the power of 15. Using our rule for rewriting this as a fraction power, our fraction power would be 15 over 5. We can simplify 15 over 5 as a 3. So 7 to the third power would mean that we would be cranking out 7 times 7 times 7. And since, of course, I don't happen to know that one off the top of my head, I would bust out my own calculator for, there we go, 343 for that final answer. For something like the next one, now we start to have a little bit more going on here. We have to address the number part of this, where we've got the fourth root of 32. We've got the variable parts that we can also split into pieces. The fourth root of a to the power 10 and the fourth root of b to the power 19. So we could deal with these separately. Now that fourth root of 32, just to address that one part at a time, we can use our calculator and try to work that out, but what we would get is a decimal answer that is not at all a nice decimal. So that leads us to believe that there's a little something else extra going on, like maybe there's a root that's left over here. And by thinking a little bit more about what we've got going on, we can actually break this apart where the 32 gets split into two separate pieces. So using the same idea that we've had for square roots, if we break things apart in a special way, that we would have one root that works out nicely and then the other root that is just simply left over. The fourth root of 16 does in fact have a nice answer of 2. The fourth root of 2, however, we cannot do anything more with that by itself. So I have no other choice but to leave that alone. And in my final answer, where I have this one extra line of room here, in my final answer, if there's any other fourth root stuff that's left over, I can combine those things together, but I can't actually simplify that in any sort of nice way. As far as my A and B stuff, well, we had a little bit of the shortcut business, and so it might be worth it to actually leave out an equal sign there in our second step and kind of say, well, what we're really talking about here is taking the 10, dividing it by 4, getting a 2, and 2/4 for that. We're going to leave that fraction because, like we've already seen, we could have some fourth root stuff that's left. So for the moment, let's go ahead and leave that fraction part alone. That's going to connect back to a fourth root, at least. What we have going on for the whole number part of this is our a will have a whole number power of 2. And that fraction will connect back to a fourth root as well as a power of 2. And what needs to be up in there is, well, again, we're working with our a stuff, so it needs to be a that's up in there like so. To use a separate color for emphasis, we're going to use that similar kind of shortcut for our b stuff, where we take that power from inside, we're going to divide that by our root number, 4, and we're going to get ourselves a 4 and 3 over 4. So that would allow us to have a regular b with that whole number power of 4, as well as the fraction giving us another root, a fourth root, with a power of 3 underneath it. And again, because we're working with b, that means that's more b stuff that shows up. So now each of these has been addressed separately. Can we do any better job of writing out all the parts of our answers in a shorter, or possibly you could say nicer looking way? Well, again, we had seen this with the square root stuff. If I've got separate square roots, then I can put those back together. Well, it's not square roots anymore, but still the same idea would apply. Let's go ahead and put these fourth roots back together again for the sake of brevity. But we're going to kick our answer off with the more normal looking parts, which would be the normal 2, the normal a squared, and the normal b power of 4. Then we'll go ahead and at the end slap on our fourth root, where all of those roots have been collected together. So underneath this single radical symbol, the single fourth root symbol, we're going to have the 2, the a squared, and the b power of 3. Each of those were pieces underneath those roots. The 2 underneath, the a squared underneath, the b power of 3 underneath. So those are all coming together into a single root for that. Back to a pure number example. Again, we've got something that we can attempt to plug into our calculator, but for working things out by hand, we have a few ways of trying to look at this using our ideas of working with roots. Excuse me. One of the options that we have is to try to simplify that numerator separately. So that would mean that we would want to try to break things apart so that we have a nice cube root. A nice cube root would be a cube root of 64, and that would leave me with a cube root of 2 that has been separated away from that. And we can come back to that denominator business in just a moment. The cube root of 64 has a nice answer of 4. The cube root of 2, I cannot do anything more with by itself. And now paying a little bit closer attention to that denominator and recognizing I have something in the numerator that matches up with something in the denominator, I can go ahead and slash out those common factors and get my final answer of 4. The alternative to working out this problem would be to combine these roots together at first and say, if we combine them together into one big old cube root, that would mean that underneath we would have 128 divided by 2. And we can simplify a 128 divided by 2 as 64. and then either we recognize or we calculate the cube root of 64 for that same answer again. So again, we've got those options, or if you're feeling frisky, you could type this into your calculator directly, or you could use fraction powers to help you type that into the calculator and see if you just automatically get a nice answer, which again, we will. So in this case, we have the calculator giving us a nice answer, but when that doesn't happen for us, we want to make sure that we have alternatives. So another example here, where we would be using some of our tips and tricks to working things out. With the way that this is automatically set up, we might lean more towards, let's take care of this division stuff before we worry about the root. If there's a way for us to simplify the division, and while we're at it, like that earlier example still popping up towards the top of the screen, we know we're going to have to separate the number stuff and the variable stuff from one another. So we might go ahead and start doing that sort of thing as well. So our cube root here, we can worry about doing the number stuff, separate it out from the x stuff, which is again separated out from the y stuff. The number stuff we can actually simplify. The 54 over 2 gives us 27. The x stuff we can also simplify, and that would give us a power of 15. The y stuff we can simplify and get a power of negative 18. This is where we're using that rule for exponents that says take the power from the top, 17, minus the power from the bottom, 2. 17 minus 2 gives us 15. Power from the top is the invisible 1, minus the power from the bottom is 19. 1 minus 19 gives us negative 18. We can use our fraction powers for the x and the y parts of this. The cube root of 27 by itself would be a 3. Our x stuff can be rewritten as power of 15 divided by 3. Our y stuff can be rewritten as power of negative 18 divided by 3, which will more directly get us to our answer, which would have the 3 followed by x power of 5 and y power of negative 6. If we were not allowed to present our answer with negative powers, we would again use our rule for those negative powers and say, all right then, apparently that y business will have to get kicked down to the denominator, so that we would have our 3x power of 5 up on top and our y power of 6 down on the bottom. So again, those rules coming in handy, especially whenever we've got the variables in the mix, trying to help us work our way through things. And still again, same tips and tricks as what we used for square roots that we're now applying to other kinds of roots. We had the comments about domain, and just to emphasize those again, because it never can hurt. The domain, the numbers that we're allowed to plug in. Even roots are the ones that we've got to watch out for. Odd roots we don't have any issues with. So when we look at this next example here, we want to find the domain. We've got a square root that's showing up here. Square root, aka the second root, that's even. Even roots, what's inside of our root, in this case that's a 1 minus x, needs to be greater than or equal to 0. It needs to be 0 or positive. It's another way of phrasing things. Well, what this gives us then is a little quick inequality to solve. If we add x to both sides, then we would get this 1 is greater than or equal to x. But that's a little awkward, and instead we could say, let's write the x first. It's far more convenient for us. x is less than or equal to 1. Notice that I've turned around the inequality symbol as well, or I could say the pointy part of my inequality symbol is beside the x, and so that sort of connection still has to appear when I write the x as the first part of my answer. So now that we've got that, again, we can, like we've done in the past, turn things into a number line and try to get ourselves a bit more of a visual here of how things look for answering our domain as an interval notation answer. So we've got the 1. In fact, let's move that up a little bit over this way. We've got our 1 that's showing up. According to our clever little comments about coloring things in, we would want to color things in the direction that are inequality symbol points. And because we have the or equal to part, that means we would want to bracket, and it's got to face the proper way. So what we've got going on here for our number line sort of answer allows us now to convert this picture and this inequality answer into an interval. Our yellow goes off to the left forever, which means parentheses negative infinity, comma in the middle. And according to our drawing, we go all the way up to 1 and then have that same bracket symbol that we saw in our drawing in order to have our finished domain answer. I don't like the way that looks, so I'm going to move that a little bit closer and things a little bit more compact there. For the other example here, to come back to that idea of domain, we have the even roots versus the odd roots. So in this particular case where we've got a cube root, or the third root, well, that's an odd root, and that means that what is underneath can be any real number and if 1 minus x can be any real number, actually what that ends up meaning for us really is that x also can be any real number. So, despite the fact that things might seem a little bit more unusual here, turns out the domain for this odd root is still all real numbers. So, nothing particularly fancy going on for those odd roots, at least certainly not at this time. It'll be a little while yet before you see anything more complicated in the way of asking for domain for either even or odd roots. So for right now, we get things that are a little bit more on the, well, they're a little bit more on the basic side of things, while we can still step it up like we've done in these two examples. But mainly, do we have an even root or do we have an odd root? That's the first main distinction that we need to recognize so that we can correctly work through figuring out the domain from there, whether it's a more basic type of problem or a more advanced type of problem that you might see in a future math class. Now again, because our purpose is to touch on different sorts of ideas that our discussion of square roots didn't quite hit, here we're going to move into our last topic about rationalizing the denominator. We had those nicer problems where we had square roots in the denominator, and that's all that we had, just a square root, nothing especially fancy. But we can take those same types of problems and we can step those up a notch by having other kinds of roots, which again, we've already seen issues with that before. So in looking at these other kinds of roots, we have to extend the idea that we've used in the past. So this is a cube root, and it has a 5 and it has a t. in order for this cube root to eventually simplify, let's pick something fun like pink, I'm going to have more stuff that gets folded into that cube root. And we'd said that the power that shows up and the type of root, if they match, then things will unlock. Because we're forced right now into having a cube root, the way to unlock that is if we can create powers of 3 on the different pieces that we have. Well, the 5 can't be unlocked until it's got a power of 3. Right now I have one 5 that's in there, written in black. In order for things to unlock, I'm going to need 2 more 5s. Well, that might be a little bit misleading. I'm going to need, more correctly, a 5 squared. That way everything will come together to eventually have a 5 with a power of 3. That same comment applies to my variable t. I already have in black a single t. I'm going to need to eventually have a power of 3 that appears, and the only way that I can get that is if I incorporate another t squared into my cube root. So the stuff in pink is the newly incorporated stuff, and what we do to the bottom, we have to do to the top. So we take the 15 that was already there on the top, and now we have to also tack on a cube root of 5 squared t squared This will allow our denominator to now have the proper sort of form that we will be able to unlock, and we'll do the unlocking part of that in just a moment. The stuff in the numerator we can tinker with just very slightly by saying 5 squared is 25. So that makes things just a tad bit friendlier looking. So, down on the bottom, now that we've got that cube root and the powers of 3 showing up, the cube root and those powers of 3 will unlock one another so that our denominator will no longer have a root in it. It will have a 5 and it will have a t, and that's all she wrote there for that denominator, which means that we have achieved the goal of rationalizing the denominator, aka we have gotten a denominator that no longer has any sort of roots or any sort of radicals showing up. Yes, our numerator does, but for right now we don't have to worry about the fact that our numerator would have roots in it. So that's something we can go ahead and just deal with. But if our goal is to get rid of the nasty element of the denominator, the nasty element of the denominator here is a root showing up, then that takes care of it. So a little extra finesse that we would have to utilize in order to handle these higher level roots. Square roots worked out pretty directly. These, well, they take a little bit more finesse to figure out how we can correctly unlock things, but it's still doable. But we can also bring those square roots back in and still complicate matters. And that would be like here in this example, where this problem, our denominator still has one square root, but that's not the only part of the denominator. It's only one term in a denominator that also has a 3 and a plus sign. That extra level of complexity requires us to use one of our other factoids, something that we had mentioned but not really made much use out of, and that's the conjugate business. We have a special sort of relationship. By multiplying conjugates, we can eliminate the appearance of square roots. So in that event that we would want to eliminate square roots, and we do, we want to rationalize the denominator. We want to get the square roots gone from our denominator. What we would use in this particular case is the conjugate of our denominator. So first term, second term are the same, change the sign in the middle, there's my conjugate. If I slap that into my denominator, then eventually my denominator is going to work out to no longer have those square roots appearing. What I do to the bottom, I also have to do to the top. So I got to work through some multiplying to get a nicer, friendlier numerator. I got to work through some multiplying to get a nicer, friendlier denominator. And eventually, what I get is I get an answer that no longer has any square root business appearing in the denominator. In fact, in this particular case, I do not get any denominator showing up at all. However, that's not the only sort of thing that could show up. I could still have a denominator, and in this next example, we'll see that we do, in fact, get a denominator still appearing. In this particular problem, again, the idea is that we would start by saying we will need to use the conjugate of the denominator. So here's my denominator. The conjugate of that denominator is going to have the same first term and the same second term, but it will need to have a different sign in the middle. So instead of a minus sign in the middle, it's going to have a plus sign. So there's my conjugate. But again, that was only for the denominator. So up in our numerator, we're also going to have to incorporate that blue expression. So up on top, we're going to need to also multiply by that square root of 3 plus square root of y, which officially means that we would be multiplying across on top, and that'll require us to FOIL here in just a moment. We're going to multiply across on the bottom as well, and we're going to FOIL, excuse me. So let's FOIL the bottom first, because that's the primary concern. Are we going to in fact get a denominator that will no longer have those square roots appearing? So if we FOIL that bad boy out, square root of 3 times the square root of 3 would give us 3. The square root of 3 times the square root of y would give us a plus square root of 3y. A negative square root of y times a square root of 3 will give us a minus square root of 3y. Looky, looky. And a minus square root of y times a positive plus square root of y will give us a minus y. So all told, that denominator, when we simplify one last little bit there, is going to give us a 3 minus y. No more square roots. So that's on target. We also have to worry about working out our numerator so that it is in a proper format. So working that out, square root of 3 times square root of 3 also gives us a 3. Square root of 3 times square root of y gives us a plus square root of 3y. Square root of y times square root of 3 gives us a plus square root of 3y. And square root of y times square root of y gives us a plus y. So that when we combine like terms there from those two middle terms, we can get a friendlier looking answer. And we got to also remember the comments that we've made about fractions in the past. We can only simplify if we have a common factor on the top and on the bottom. That numerator, we just saw that that came from stuff that had a factored appearance to it. I do not have a factor on the top that matches with this nice denominator I just achieved, which means that I do not have any slashing that I can do. I am stuck with this as my final answer. At the very least, though, there are no more square roots that appear in the denominator. So for what that's worth. And again, that's what we have to accomplish when they tell us specifically to simplify a problem like this, or if they're more specific and they say that we need to rationalize the denominator. So that takes care of some of the additional arithmetic and also the domain concerns in there about other kinds of roots than just the square roots, so that you are now better equipped to deal with all the different kinds of problems that might be thrown at you regarding simplifying, regarding adding, subtracting, multiplying, and as far as dividing goes, we specifically refer to that more as rationalizing the denominator.